I like this experiment. It was done by Émeric Plancher at EDF in France, in Fontainebleau, and it's a 4-point bend test. The nice thing about a 4-point bend test is that along the axis of the curvature, it's neutral. There is no tensile or compressive strain. It's zero strain all the way along there. At right angles to it, linearly distant from the central axis, it deforms linearly in the elastic mode. When you get far towards the edges, if the sample is bent enough, those edges are under maximum strain and will go plastic. So it will no longer be linear and it will deviate from the linearity. That's the setup. Now here are just some of the results from this data set. I'm showing two data sets. One is using a 1K by 1K camera. And we're measuring here the, it's the strain along the axis. It's parallel to the axis. So it should vary linearly with distance from that 0 point. So here's the scatter of the data. That's 2 parts in 10,000. That's a strain of 2 parts in 10,000. It goes up to a maximum 4 parts in 10,000. The lower one shows the identical specimen measured in a different microscope, but using a 2K by 2K camera. And then we see exactly the same data, but the noise is much, much lower, illustrating the advantage of using a 2K by 2K camera as to a 1K by 1K camera. And by the way, the resolution of how far, how small a distortion we can measure over, it comes out to be 2 microns in the 2K by 2K camera. But you'll notice the slope of the 2 lines turns out to be the same. So that is an absolute measure of strain. We know how it should behave. Is the amount of deformation what you expect? And just as in the first days of EBSD, everybody compared EBSD results with X-ray data. So this is being compared with X-ray data. This is the blue line is a micro-Lowy synchrotron radiation data on the same specimen, and you see the linearity of the EBSD measurement and the micro-Lowy over that distance is absolutely identical. When you get into the work-hardened regions, and that's what I'm showing here and here, they differ. And I'm not surprised, because you can't be exactly certain that on the synchrotron radiation, when it's placed in the beam, you're looking at exactly the same trace normal to the line. So when it gets into the plastic region, you're looking at slightly different plastic deformation. So that is a finite proof of the performance of this HR EBSD technique. Now, here is some data from Saji Suzuki's lab in Japan. He's kindly let me show this before. Here's an ordinary IPF map, and here's the detail. And what is nice about this data set is it's part of an in situ set of tensile testing where EBSD patterns were recorded along the elastic line up into the plastic region. I just want to draw your attention to the fact that at the bottom, when you haven't strained it at all, it's all in the green. There is 0 strain. Just a little bit of residual strain in that grain up here and some a little bit down there, but virtually nothing. As you'd expect, it's not strained. But once you start going up the elastic curve, you see we're going into this yellow region here. The strain, so the measured strain is what you expect from the tensile curve. But as soon as it goes plastic, things start to happen in the microstructure. First of all, you'll notice that this grain here has gone into compression. So the plastic relief of the elastic strain has allowed the stress distribution surrounding it to push this one into compression here. And on here, for example, you can start to see the strain build up on lines, and those are obviously the slip lines. Now here's another couple of examples. This one from a paper with Wilkinson and Britton, which I love, because it shows the stress concentration against a dislocation pileup. Things we've talked about ever since we were undergraduates and never seen it experimentally proven. But here it is. Here's a grain boundary. Along here, you see no strain. That's because you've got very few dislocations there, and you only need a few dislocations piled up against a grain to have a concentrated stress or strain ahead of that pileup. We all know that. And it follows a very well-defined law, as shown by the red line here. And Ben and Angus's data fitted to this show the change in stress with distance ahead of that pileup. Now we go back to this example here. This is given to us by Brett Dunlop, and for which we're very grateful. And I said before, on the HR EBSD map, we saw something going on at this boundary here and that boundary here, but not there. And now we're looking at this is shear stress, and I'm looking at the maximum tensile load, stress in the setup. They're called principal stresses. And I'm looking at the principal stress because this stress or deformation ahead here is not as neat as a single dislocation pileup. Here we're looking at all three principal stresses. You'll have a principal stress positive and one negative, because when something strains, there's always a strain ellipsoid associated where the axes of deformation do not change direction, only their magnitude. And they're known as the principal stresses, and this is a very useful way of representing your damage in a material. And also, one can map the von Mises stress criterion. I don't like to think of it the way we map it as the von Mises stress criterion. It's an energy criterion, and you can relate. This is energy per unit volume, and now if you think of it as an energy per unit volume map, then you see where your energy is building up. I don't consider, things around the nano indents are not of importance. It's what's going on at the grain boundary here. But you see, you've got energy build up between this grain boundary and that indent, but nothing happening on the other side. And I find that very interesting. So we can calculate from the strain gradient the GND density. And using, without sensitivity of 1 part in 10,000, you can measure the dislocation density down to 10 to the 12. That's 1 micron between each dislocation, which is the annealed-in dislocation density. So where it is in the green, it's at the annealed-in density, and we're starting to see things round about 1 order of magnitude bigger than that. And of course, you expect this dislocation density to be greater at the boundaries as it is, and we're looking at the total density there, the edged contribution and the edged contribution there. And you can look at the densities of the individual dislocation types as well. Well, to put all of that together, I go back to that work by Suzuki and Fukino, and I'm looking at a detail of this grain boundary here, and this grain here, and we see the slit lines. The slit lines fall short of this grain boundary. That means the dislocations didn't get to the grain boundary. That means they're in a pile-up configuration. They just don't, there are not enough of them to produce the slit lines. And what we see in the strain map is we see a build-up here on that side of strain, but we don't see any dislocations on that side. The dislocations are all on this side. And by looking at the sign of that, you can tell whether, by looking at whether this is in compression or tension, you can tell which type of dislocation is involved in that release from the pry-ups. This is an old slide of Angus Wilkinson. It was taken to show that we could accurately predict or measure the strain in germanium silicon. So this green line is silicon substrate, and these are the E11, E22, E33 measurements along there. And when you get into the germanium silicon, it goes tetragonal, and you see the C-axis has come up here, and the A and B axes are down here. So we can easily see the tetragonal distortion in that germanium silicon. But I'm using that as an introduction to a much more difficult case, and that is where the tetragonal distortion is very small. And you cannot use the fact that it's strained because this is a naturally, I'm looking at PZT, and it's naturally strained. It is naturally distorted as a tetrahedral structure. So you can have these three configurations. That one where the c-axis is along there in one domain and c-axis along there in a second. Here we have a c-axis there, a c-axis there, like that. Now, this, what we measure, remember, what we measure is A11 minus A33 and A22 minus A33. I said that right at the beginning. That's what we actually measure. So we measure A11 minus A33, A22 minus A33, and we know in this configuration the reference C is bigger than A, and the axis A is, that's a 3, so we want this one. A here is the same as that. So we can get, for these different configurations, these two features which we measure, delta 1, delta minus delta 3, delta 2 minus delta 3, and this, they are uniquely large, intermediate, and then going negative. So it tells you which one is, if you measure that experimentally, it tells you which one is the c-axis. And there it is as an experiment. Here is the A grain, and if you find where the real axes are, the 100 type axes are in space, and then look to see what the ratio between the X, Y, and Z axes are, you can determine which is the true C-axis, and you say it's the light green is the C-axis in this material, and the dark blue is the A or the B.